find somewhere comfortable. You don't need to follow any of this closely. You don't need to hold on to the details or remember a single word come morning. Just let the sounds arrive the way a distant radio drifts through a wall, present and soft, and not quite demanding anything. We have a whole hour and nowhere else to be. If today was hard, you can set it down now. Whatever you carried through the hours since you woke, the small frustrations, the larger worries, the things that went unsaid or went wrong, none of that needs to come with you into this quiet. The night is patient. It has been waiting. Tonight, we're going to travel somewhere extraordinary, not far in the way that requires effort, but far in the way that wonder sometimes takes you, gently away from the ordinary, into something that has been true all along, right above your head, right there in the light that fell through your window this morning. We are going to follow that light back to its source and find something stranger and more beautiful than you might expect. You don't need to concentrate. You don't need to understand every part. The words will come and go like the tide, and whatever reaches you will be enough. We're in no hurry tonight. Think of a morning when the sun came through a window and landed on your face. Not a dramatic sunrise, nothing that required you to do anything. Just that quiet moment when you became aware of warmth on your skin, a gentle pressure of light, the way it makes the inside of your eyelids glow faintly orange if you turn toward it. Most of us have had that experience so many times that it has become almost invisible, the way breathing becomes invisible. The sun is there. It is warm. Of course it is. But follow that warmth back for a moment. Follow it away from your skin, back through the window glass, back out into the open air, back up through the atmosphere where the light is still traveling fast and clean and vast. Keep going, out past the clouds, past the satellites, past the moon hanging in its slow orbit. Keep going further, across a distance so large that if you drove it at highway speed without stopping, you would be driving for more than 170 years. Out there, at the end of that journey, is the thing that sent the warmth to you. A star, our star. The sun is enormous in a way that is genuinely difficult to hold in the mind. More than 1 million Earths could fit inside it. Its surface is always moving, always churning, great arcs of hot gas rising and falling in slow motion. And at its heart, at the very center of all that weight and heat, something is happening. Something has been happening for nearly 5 billion years. Something that, by every rule of ordinary physics, the physics of billiard balls and rolling stones and objects that behave the way objects are supposed to behave, should not be possible at all. The sun is hot, 15 million degrees at its core. A temperature so far beyond anything we experience on Earth that the number stops feeling real. And yet, even that extraordinary heat is not enough. Not by the rules we once thought governed everything. By those rules, the particles at the sun's heart do not have enough energy to do what they are clearly doing. The sun, in the most literal sense, should not shine. And yet the warmth was on your face this morning. There is something happening inside the sun that goes beyond the ordinary rules of how things push and pull and collide. Something that operates at a scale so small it is almost impossible to picture. At the level of individual particles, far smaller than atoms, far smaller than anything with a name you could point to in a room. Something that belongs not to the physics of the world you can see and touch, but to a quieter, stranger physics that lives underneath. We don't need to name it yet. For now it is enough to carry the question, the way you might carry a smooth stone in a pocket without thinking about it. The sun is shining. By the old rules, it shouldn't be. Something else is at work. The light that found your face this morning has been traveling for about 8 minutes. That part, at least, is swift. But the story of how it came to exist at all is far older and far stranger. And it begins in a place of almost unimaginable pressure and heat, where the rules of the universe quietly bend themselves in ways that even now take the breath away. That is where we are going tonight, slowly, without any hurry at all. To understand why the sun is strange, it helps to first understand the rules it appears to be breaking. Imagine a ball rolling across flat ground toward a hill. The ball is moving, and moving things carry energy in their motion. The faster they move, the more energy they have. If the hill is low enough, the ball has enough energy to climb it, crest the top, and roll down the other side. But if the hill is too tall, the ball slows, stops somewhere on the slope, and rolls back the way it came. This is not a complicated idea. It is the kind of thing you understand in your body before you understand it in your mind. You have felt it yourself, cycling toward an incline, feeling your momentum drain away. This is how the old physics, the physics of the world we can see, describes almost everything. Objects have energy. Barriers require energy to cross. If you don't have enough, you don't cross. You come back. Now bring that image down to something unimaginably small. A proton. A proton is one of the tiny particles at the heart of every atom, and the sun's core is made almost entirely of hydrogen, the simplest atom there is, which means the sun's core is essentially a vast, dense, furiously hot sea of protons. For the sun to shine, these protons need to fuse together. They need to get close enough that a different force, a very short-range force that only operates at extremely tiny distances, can grab them and bind them into something new, releasing energy in the process. That release of energy, accumulated across billions of events every second, is what the sun is. But here is the problem. Protons are positively charged, and positive charges push against each other. The closer two protons get, the harder they push apart. It is as if the hill in our earlier image gets steeper. The closer you get to the top, and steeper still, and steeper, until it becomes something more like a wall. To push two protons close enough together for them to fuse, you need to overcome that wall of repulsion. Heat is the way you do it. Heat, at the level of particles, is just movement. Fast, frantic, constant movement. The hotter something is, the faster its particles are flying around, and the faster they're flying, the harder they collide. In principle, if you make something hot enough, the collisions become violent enough to push protons past the wall and into each other's arms. The question is, how hot is hot enough? When physicists in the early 20th century calculated the answer using the classical rules, the same rules that describe the rolling ball and the hill, the number they got was staggering. Something like 60 to 100 times hotter than the sun's core actually is. By those calculations, 15 million degrees is nowhere near sufficient. The protons in the sun's core are moving fast, yes, but not nearly fast enough to batter their way over the repulsion barrier and fuse at the rate we observe. And yet fusion is clearly happening. The sun is clearly shining. The energy is clearly arriving at Earth. You can hold your hand up and feel it. For a while, in the early decades of the 20th century, this was a genuine puzzle. Some physicists wondered if the sun was powered by something else entirely, by gravitational collapse perhaps, the slow shrinking of a massive object releasing energy as it fell inward. But the numbers didn't work. A sun powered only by gravity would burn out in tens of millions of years, not billions, and the geological record of Earth makes clear that the sun has been shining steadily for an incomparably longer time. The sun is old, reliably, patiently old. Something was missing from the picture. The classical rules, solid, reliable, beautifully tested in every other context, were telling a story that didn't match the evidence sitting in the sky above everyone's head. The ball was getting over the hill without enough energy to do it. The protons were getting close enough to fuse without enough speed to batter past the repulsion. The rules were not wrong exactly. They were incomplete. They were the rules of a world seen from the outside, the world of things large enough to hold and observe. And deep inside the sun, in a place of crushing density and ancient heat, something was happening that the rules of the large world simply could not account for. The missing piece would arrive from a completely different direction, not from astronomers looking outward at the sun, but from physicists looking inward past atoms, past the nucleus, into a realm where the very idea of a particle in a place begins to quietly dissolve. The late 1920s were a strange and fertile time in physics. The old certainties were coming apart. For 2 centuries, the picture of the physical world had been one of objects with positions and velocities, governed by forces that could be calculated precisely. You knew where a thing was. You knew how fast it was moving. You could predict, in principle, exactly where it would be at any future moment. The universe was a machine, intricate and vast, but a machine nonetheless. Its behavior in principle knowable, its future in principle calculable. Then, in the mid-1920s, a new set of ideas began to arrive, and they did not fit the machine. An Austrian physicist named Erwin Schrödinger published an equation in 1926, a beautiful, strange piece of mathematics that described particles not as objects with positions, but as waves of probability. The equation didn't tell you where a particle was. It told you where a particle was likely to be found. And crucially, this wave of probability didn't stop at barriers. It didn't simply halt and turn around the way a ball does at the top of a hill. It can't climb. It spread. It seeped. It extended into regions that the particle, by classical reasoning, had no business being in at all. The implications took a little time to surface. One of the first people to see what they meant for the physical world was a young Russian physicist named George Gamow, working in Göttingen in 1928. Gamow was 24 years old, curious in the wide, unhurried way of someone who has not yet learned to narrow their attention, and he was thinking about a problem that had been bothering physicists for years. Certain atomic nuclei are unstable, sometimes quickly, sometimes over thousands of years. They shed a small cluster of particles, releasing energy as they do. The puzzle was that these clusters, by all classical reasoning, should not be able to escape. The forces holding the nucleus together form exactly the kind of barrier we described in the last chapter, a wall of energy that the escaping cluster, by rights, does not have enough energy to climb, and yet it escapes. Patiently, eventually, it escapes. Gamow realized that Schrödinger's wave equation offered an answer. If a particle is not a hard, definite object, but something more like a spread-out wave of probability, then that wave can extend beyond the barrier. The particle doesn't smash through the wall. It doesn't climb over it. It simply has a small but real probability of being found on the other side, and sometimes, when the particle is looked for, on the other side is exactly where it is, as if the wall had never been there at all. He worked out the mathematics over the course of a few weeks. The predictions matched the observed behavior of unstable nuclei with a precision that was, by the standards of the time, astonishing. Gamow published his results in the autumn of 1928, and quietly, without fanfare, one of the deepest ideas in all of physics had found its first clear application in the real world. The same year, 2 British physicists named Ralph Fowler and Lothar Nordheim were arriving at closely related ideas about electrons in metals, and in Russia, Leonid Mandelstam and Mikhail Leontovich were working along similar lines, independently, in a different city, in a different language. What all of these people were touching from different angles was the same quiet revolution, that matter at the smallest scale is not a collection of tiny solid objects. It is something more like a collection of possibilities smeared gently across space, with no sharp edges and no precise address. A particle is not a marble. It is more like a fog, thicker in some places, thinner in others, but never entirely absent anywhere and never entirely confined. This was a shift in understanding so fundamental that it is still not entirely easy to absorb even now. The world we live in feels solid. Objects are where they are. Walls are barriers. The ball either has enough energy to climb the hill or it doesn't. But that solid, reliable, everyday world is built on top of something far stranger, a substrate of blurred, probabilistic, seeping reality. where the rules are gentler and the possibilities are wider. Gamow saw it first in unstable nuclei, but the same logic, as a few sharp minds quickly noticed, could be pointed in a different direction, not at particles escaping from nuclei, but at particles trying to get in, trying to get close enough to fuse. The sun, still puzzling and inexplicable by classical means, suddenly had a candidate for its secret. Let's stay here for a while, in this slow and important idea, and let it settle fully before we go further. Imagine you are trying to find a friend in a foggy city. You know roughly which neighborhood they're in, but the fog is thick, and they could be on any of several streets. The fog itself isn't random in a useless way, it's denser in some places than others, and the denser the fog, the more likely your friend is nearby. If you reach out and touch something solid, you've found them. But until that moment of contact, they are not precisely anywhere. They are distributed across the possible streets, more probably here, less probably there, but genuinely, physically, not pinned to one spot. This is, in a carefully limited sense, what a proton is like. Not metaphorically, actually. Before it interacts with something, before it is measured or detected or collides with another particle, a proton exists as what physicists call a wave function, a spread of probability across space. Denser where the proton is most likely to be found, thinner at the edges, but the edges do not stop sharply. They fade. They taper away into regions where the proton is unlikely, but not impossible. Now imagine placing a barrier in this foggy city. A wall, let's say, running across several streets. For a solid object, a wall is final. You either have enough energy to climb it, or you turn back. But for a fog, for something that doesn't have sharp edges, a wall is more like a filter. Most of the fog is blocked. Most of it piles up on one side, unable to cross. But a little of it seeps through. The fog is thinner on the other side, much thinner, but it is there. And if you reach through the wall and find your friend, they are genuinely on the other side. Not by breaking the wall, not by finding a gap, by being the kind of thing that doesn't have to be entirely on one side of anything. This is tunneling. The particle doesn't drill a hole. It doesn't shatter the barrier. The barrier remains intact and whole. The particle simply has a probability of being found beyond it, and sometimes, not often, but sometimes, that is where it is found. The word tunneling is a metaphor that has stuck, and it is useful enough, but it carries a slightly misleading image of something moving through the interior of an obstacle. The truer picture is that the particle was never entirely confined to one side in the first place. Several things affect how much of the fog gets through. The thickness of the barrier matters enormously. A very thin wall lets far more through than a thick one. The height of the barrier matters too, in the sense of how much energy would classically be required to cross it. And the mass of the particle plays a role, because heavier particles have probability waves that are more tightly compressed, less spread out, and so less of their fog extends into the barrier in the first place. Protons are relatively heavy as subatomic particles go, which is part of why the tunneling probability for any given pair of them is so small. But small is not zero. There is something worth pausing on here in the quiet of the night. What this picture tells us is that the universe, at its most fundamental level, is not made of things. It is made of tendencies. The solid world we inhabit, the world of floors and walls and hands and faces, is an emergent property of something far more fluid underneath. A world where location is a matter of probability, where barriers are permeable, where the hard certainties of everyday experience are approximations of something softer and stranger. The physicist and author Richard Feynman once said, with characteristic directness, that nobody understands quantum mechanics. He didn't mean that the mathematics was obscure. The mathematics works with extraordinary precision. He meant that the picture it paints of reality is so different from the picture our senses give us that there is no comfortable way to fully reconcile them. We can use the equations. We can build technologies from them. We can predict outcomes with breathtaking accuracy. But to truly see the world as the equations describe it, as a place of smeared probability and seeping fog, requires a kind of imaginative surrender that doesn't come naturally to minds built for the solid world. And yet, the fog seeps. The proton finds itself on the other side of the wall it could not classically cross. And in the heart of the sun, this happens over and over and over in numbers so vast that the light from it has been warming a small blue planet for nearly 5 billion years. Go deep now, deeper than any instrument has ever directly reached, deeper than light itself can carry a message from, because the interior of the sun is so dense that light cannot travel freely through it. We are going to the center. The sun's core is not a place that accommodates easy description. The density there is roughly 150 times the density of water, heavier than gold, heavier than lead, heavier than almost anything you could hold in your hand. And yet it is not solid. It is a plasma, a state of matter in which atoms have been stripped of their outer structure by the ferocity of the heat, leaving bare nuclei, bare protons, in the case of hydrogen, moving at extraordinary speeds through a sea of freed electrons. Everything is in constant motion. Everything is colliding constantly. The temperature is 15 million degrees, which means the average proton is moving at something like a few hundred kilometers every second. In this environment, protons are encountering each other at a rate that is almost meaningless to try to picture. Each proton collides with another proton an almost uncountable number of times every second, and at each encounter, the two protons feel that repulsive push. The electrical force of like charges, shoving them apart before they can get close enough for the stronger, shorter-range force to take hold and bind them. By classical physics, none of these encounters should end in fusion. The protons are fast, but not fast enough. The barrier is too high. They should all bounce away, every single one of them, and the sun should be cold and dark. But the protons are not hard little marbles. They are fogs. And when two fogs approach each other, the edges of each one can seep into and through the barrier of repulsion between them. For any given encounter, the probability of tunneling occurring, of the two protons finding themselves on the fused side of the barrier, is extraordinarily small. The numbers involved are almost poetic in their extremity, something like 1 chance in 10,000 trillion trillion, a number so small that writing it out in full would take a while. And yet, the sun contains an almost incomprehensible number of protons, somewhere around 100 followed by 55 zeros, and they are all colliding constantly at rates that make any humanly meaningful number feel quaint. When you multiply even a vanishingly small probability by a number that vast, operating over timescales that long, the result is not nothing. The result is billions of fusion events every second, each one releasing a small packet of energy, all of them together adding up to the 400 trillion watts that the sun radiates continuously into space. When two protons do manage to fuse, when the fog of one overlaps the fog of the other at just the right moment and the tunnel opens, what happens next is the beginning of a chain. The two protons bind together, and in the process one of them changes its nature, becoming a neutron, and a small particle with almost no mass and no charge is released and goes streaming away at nearly the speed of light. The remaining pair, one proton and one neutron, is now a different thing entirely, a heavier form of hydrogen, and it will eventually meet other particles and fuse again and again in a slow sequence of steps that ends, after several interactions, with 4 protons having become a single helium nucleus and a small amount of mass having been converted entirely into energy. That conversion, mass becoming energy, is the sun's fire, not burning in the chemical sense, not oxidation or combustion, but something far more fundamental. Mass itself, the stuff of matter, trading its existence for pure energy. And the rate at which this happens is determined, at its root, by tunneling, by the quantum fog seeping through the barrier, by the universe quietly bending its own rules at the smallest possible scale. What is perhaps most striking about this process is its patience. The sun is not burning fast. For any individual proton, the average wait before it successfully fuses with another is something like 5 billion years. 5 billion years of collisions, each one failing, the fog approaching and retreating, until at last the rare moment arrives. The sun burns slowly. It burns the way deep time burns, not in a rush, not in a flash, but in a long, unhurried exhale that has been going on since before the earth existed and will continue long after it is gone. The energy released when two protons fuse is not immediately the warm light that reaches your window. It begins as something far more energetic, a very short wavelength form of radiation, a kind of light far too intense and penetrating for human eyes, released at the very center of the sun. And what happens to it next is one of the stranger and more quietly beautiful facts in all of astronomy. The sun's interior is not empty space. It is extraordinarily dense. That plasma of protons and electrons packed together at pressures that have no earthly analogy. Radiation trying to travel through this material does not travel in a straight line. It is absorbed by a particle, re-emitted in a random direction, absorbed again, re-emitted again, absorbed, re-emitted, over and over and over. The path it takes is not a journey but a stumble, a random walk through a vast crowded room, bouncing from wall to wall with no clear direction, making almost no net progress at any given moment. How long does this take? The answer is one of those facts that tends to stop people. The best current estimates suggest that a photon, a single packet of light, created in the sun's core, takes somewhere between 10,000 and 100,000 years to make its way from the center to the surface. Some calculations have suggested it could be even longer. The uncertainty in the number is itself vast by human standards, but even the lower end of the range is staggering. 10,000 years of bouncing, scattering, being absorbed and re-emitted in a random direction, slowly, incrementally diffusing outward through a body of almost incomprehensible density. 10,000 years ago, human beings were learning to farm. The first permanent settlements were appearing along river valleys. The Ice Age had recently ended and the world was greening. And the light that fell on your face this morning was, around that time, somewhere in the middle of the sun, beginning the last leg of its long, stumbling journey outward. When it finally reaches the surface, when the density drops enough that radiation can begin to travel freely, it is released into space, and then it moves at the full, extraordinary speed of light. 8 minutes later, it reaches Earth. 8 minutes. After perhaps 50,000 years of slow diffusion through the solar interior, it crosses the final distance between the sun and us in the time it takes to make a cup of tea. That asymmetry is worth sitting with. The patience of the interior, the swiftness of the final crossing. And now widen the lens. Step back from our own sun and look at the sky on a clear night. Every point of light you can see is a star. Most of them are suns like ours, or larger or smaller, some burning hotter and bluer, some cooler and redder, but all of them shining by the same process, all of them lit by the quantum fog of protons seeping through barriers they classically cannot cross. Every star in the sky, every galaxy containing hundreds of billions of stars, every galaxy in a universe containing hundreds of billions of galaxies. The universe is lit by tunneling. That is not a poetic exaggeration. It is the plain description of what is happening. The light of the cosmos, all of it, from the nearest star to the most distant galaxy whose light has taken billions of years to reach us, is the accumulated result of particles doing something the old rules said was impossible. The universe found a way. Not by breaking its own rules, but by having deeper rules that the surface rules were only approximating. And in those deeper rules, there is room for the fog to seep and for the stars to burn. Somewhere out there in the dark, at distances so vast that the light now arriving at Earth set out before our planet existed, other suns are burning with the same patient quantum miracle. The universe has been doing this for a very long time. It was doing it long before there was anyone here to notice. The same process that lights the stars is not confined to stars. It is closer than that, much closer. It is, in fact, woven into the fabric of the everyday world in ways that touch history and geology and the living cells of every creature on Earth, including, in all likelihood, the cells of your own body right now as you rest. Consider the quiet process of radioactive decay. Certain atomic nuclei are unstable, not because they are damaged or abnormal, but simply because of the particular arrangement of the particles inside them. Over time, they shed a small cluster of particles, releasing energy and transforming into a different kind of atom in the process. This is what Gamow was studying in 1928 when he first worked out the mathematics of tunneling. The cluster of particles inside the nucleus, it turns out, is in exactly the situation of a proton approaching the fusion barrier in reverse. It has the energy to exist where it is. It does not have the energy to classically escape, and yet it escapes. The fog seeps outward through the barrier that should contain it, and eventually the particle is found outside. What makes this practically extraordinary is that radioactive decay happens at a rate that is determined entirely by the quantum probability of tunneling, and that rate is exquisitely consistent. A given unstable nucleus has a fixed probability of decaying in any given moment, and this doesn't change with temperature, pressure, chemistry, or any other external condition. It is a pure quantum clock, ticking at a rate set by the geometry of the barrier and the fog. This consistency is the basis of radiometric dating, the method by which we can determine the age of ancient objects, ancient rocks, and ancient organic material with remarkable precision. When a living thing dies, certain unstable atoms in its body begin decaying at their fixed, known rate. By measuring how much of the original material remains and how much has transformed, we can calculate how much time has passed. The age of a bone, the age of a piece of wood from an ancient fire, the age of the rocks beneath our feet, some of which have been dated to more than 4 billion years. All of this is possible because tunneling happens at a rate that never varies, never drifts, never surprises. It is perhaps the most reliable clock the universe offers. But the story gets stranger and more intimate than ancient rocks. In recent years, researchers studying the chemistry of living things have begun to find evidence that tunneling plays a role inside the body itself. Enzymes are the molecular machines of life. Proteins folded into precise shapes that speed up the chemical reactions that keep cells functioning. Without enzymes, most of the reactions that sustain life would happen far too slowly to be useful. Enzymes make them fast. The question of how they do this has been studied for decades, and the classical answer, that the enzyme's shape brings the reacting molecules closer together and lowers the energy needed for the reaction, is well established. But some researchers have found that in certain enzymes, the reaction happens faster than even that explanation can fully account for. The leading candidate for the extra speed is tunneling. In some of these molecular machines, it appears that hydrogen atoms, the lightest atoms, the ones with the most spread out probability fog, are not so much crossing the energy barrier between states as seeping through it. The reaction happens not because the atom climbs over the hill, but because it finds itself on the other side without having made the climb. This is still an active area of research, and the full picture is not yet settled. But the early evidence is compelling, and the implication is quietly extraordinary. Life itself may be running, in part, on quantum tunneling. The processes that break down food, that copy genetic material, that drive the reactions in every cell of every living body, some of these may depend on the same phenomenon that lights the stars. The same fog seeping through the same kind of barrier at a scale almost impossibly small in the warm interior of a cell, in a body lying in the dark. You are, if this is right, not merely warmed by quantum tunneling. You are, in some small but real sense, running on it. The night is very quiet now. If you have been drifting in and out through the earlier chapters, that is perfectly fine. The ideas have been moving around you like slow water, and whatever has reached you is enough. We have arrived at the last part of the journey, and the pace here is slower still. We have traveled a long way tonight. We started with warmth on skin, with the simple and ancient fact of sunlight, and we followed it back through space and time to its source, to a place of crushing heat and ancient density where the rules of ordinary physics run out and something stranger takes over. We found that the sun shines not because its heart is hot enough by the old rules to force its particles together, but because those particles are not the hard, definite, well-behaved objects the old rules imagined. They are fogs, spread out possibilities, and the fogs seep through barriers that hard objects cannot cross, and in the seeping, energy is released and the star burns. We found that this same seeping is what makes certain atoms unstable, and that the patience and consistency of their decay has let us read the age of the world, the bones of ancient creatures, the layers of ancient stone, the slow autobiography of a planet written in the language of quantum probability. We found hints that the same process might be working inside the living cell, inside the molecular machinery of life, possibly inside you. And now it is very late, and the sun is on the other side of the world, and the room you are lying in is dark and still. There is something worth resting in as you settle toward sleep. We live on a planet that exists in a habitable zone around a stable star. That star has been burning steadily for nearly 5 billion years and will continue for another 5 billion or so. Long, patient, unhurried. It burns not by brute force, but by a kind of quantum grace, a process that should by rights be impossible, but is made possible by the deepest nature of matter. The universe did not have to be this way. The rules did not have to include this particular softness, this particular tendency of the very small to seep and spread and find their way through what should be impassable. But the rules do include it. The universe is built with this flexibility at its foundation. And because of that flexibility, because of the fog and the barrier and the tiny, patient probability, the stars turned on, billions of them, in billions of galaxies scattered across the dark. And around at least one of them, a small planet formed at just the right distance, and liquid water gathered on its surface, and life began. And after a very long time, creatures appeared who were curious enough to lie awake at night and wonder about the warmth they had felt on their faces that morning. The light that touched you today was born in the sun's core long before your ancestors were born. It spent thousands of years wandering through the dense interior of a star, bouncing and scattering in no particular direction, before finally escaping into open space and crossing the last distance to you in 8 swift minutes. It arrived having made that whole improbable journey, and before the journey, the fusion event that created it, made possible by a proton that was not quite where it was supposed to be, not quite contained by the barrier that should have held it. You are here because the universe is stranger than it looks. You are warm because matter, at its smallest scale, refuses to be entirely pinned down. You are alive and resting and breathing slowly in the dark because billions of years ago a star began to shine in a way that classical physics cannot explain, and kept shining and kept shining and kept shining with the long, unhurried patience of something that has all the time in the universe and no particular rush. The sun is still out there, on the other side of the earth, angled away from you now, but burning with the same quiet process it has always used, the same fog, the same barrier, the same ancient improbable seeping of possibility through what should be solid. And you are here, in the dark, which is only the absence of that light for a little while. The day is already far behind you. Whatever you carried into this hour, you can let it go further now, the way a hand slowly opens. The universe has been tending to itself for a very long time without your help, and it will continue through the night. Drift now, if you are ready. The stars are out. They are all of them shining. Sleep well.